Alexey's been coming to these things almost as long as we've had them, I think.
Not quite as long, I think. But
Yeah, within the first year or so, I think. So,
something like that.
finally talked him into giving us a talk. So, I will simply let him start.
Yeah, so I'm Alexey. I've met a fair number of you at these things before. So I figured I'd tell you what I'm up to professionally. So the talk is called Probabilistic Programming, but what the enterprise is about is making programs that have a little bit of what you might boldly call intelligence. And I'm going to be very concrete. I want to live code one for you. Very small toy problem, toy program, very short. And
Very short.
Yeah.
Fast though.
And if the probabilities show up, they'll only show up in how the thing works, rather than being front and center, as one might have expected. So it's going to be written not in Haskell, but in VentureScript, which is the scripting language for the venture platform that I'm working on. You can learn about it over there. We released, latest release was in January. You can download it, play with it if you want. VentureScript is basically scheme-like, so I expect it to be relatively easy to read. Actually, it's two front-end syntaxes that I'm going to use as scheme-like. If not, just think prefix notation and parentheses. You'll be fine. And, ask questions if you want me to interpret what's going on. I can.
Sorry, before, and let me know if you want to defer this. How does this differ from things like Church and Anglican being a scheme-like probabilistic programming, like a Lisp that is also a probabilistic programming language?
It descends from a similar intellectual heritage. Many of the same people are involved.
Mm-hmm.
So the PI at the lab was one of the co-authors of Church. The people who did Anglican were, ironically enough, one of our subcontractors, our DARPA grant for a while, so it's all very incestuous. Mm-hmm. And actually, by the end of the talk, I will have shown a glimpse of what's really fundamentally different. So, without further ado, let's get to the example. That's right. I may not have. Darned. So the example is going to be about flowers. Irises, to be exact. What you're looking at over there is a plot of remarkable objects that gets to be called the Iris Dataset. That is actually a unique name. The dataset was collected in 1935 by one Edgar Aderson and popularized by one Ronald Fisher in 1936 as an example of a statistical technique that Fisher was interested in promulgating, and the dataset has been used as a test for inference methods ever since. Unfortunately, I didn't think to download a picture of an iris, but
no one ever does.
Is it the flower?
yes, that's right. Actually, if you Google image search for the Iris dataset will show pictures of irises labeling what these axes mean. should have just done that before I came, but I was dumb. But so, 4 aspects of the flowers were collected. The lengths and widths of the petals and the sepals, which are 2 different parts of the flower. And every point you see is a projection on the 2 relevant dimensions of that flower. Every flower will generate 1 point in every block on the grid. This is a way to plot a 4D object. And this is sort of what it looks like. Give you, so this is the shape of this data. I take no credit for the visualization. This data set is sufficiently famous that this is actually a cribbed example from the documentation of D3 on this data set. But, so I didn't do the box. Just took it. Anyway, that's what we got. So, this is the audience participation moment of the talk. Looking at that, can you make up a plausible other iris on these dimensions? How long are the sepals going to be of your plausible iris? Oh, I should say these are at centimeters on all the dimensions.
New species?
No, new individual.
You can see the 6 or something.
6,
in the
yeah.
middle of the.
Great. So 6 here. How wide?
3-ish.
3-ish. So that's there on this block, which also puts it here on this block. Great. How long are the petals?
Let's go with, you could go with 2 and hit the group there.
2.
You can hit the little cluster down on the bottom, or you can hit the big block up top.
Yeah.
So actually, if you're paying attention, this is actually the same as this.
That would be
But
an
anyway.
issue.
Point
I'm
is,
not sure what the relationship between the graphs of the
so
horizontal and vertical, or is that the wrong way to look at it?
so this square is a 2-dimensional projection. These 2 are mirror symmetric, and this square is the orthogonal 2-dimensional projection.
If you want to know what a square is, go left or right, and you'll find a label, and that tells you what the
This
vertical
is the petal width dimension. This is as is this.
Oh, okay.
And this is the petal length dimension, as is this.
Okay.
So this is width against length of petals, that's width against length of sepals, and either one of the... So a point in both of these boxes is sufficient to perfectly characterize one plant.
Okay, but just correct me if I'm not sure I'm following properly. We can't just pick, a point relatively close to the clusters in each separate feature because we don't necessarily know the conditional dependencies between the features.
Yeah, but
Like if we pick one in the small cluster on petal
Yeah,
length.
so you do need to know this.
Okay, yeah. So we have a visualization that's all.
Okay.
So if you're going to be 6'3" over here, you probably want to be up there. But, point is, you can do this. You can make up irises, and you'll make up different ones every time I ask. And different people will make up different ones. You can also do other related things. You can, if I say, okay, here's a candidate iris, it's here and here. You're going to say, no, good, don't like that one. Much worse than here and here. And so you can evaluate.
characterize what pedal, the iris with the pedal link past the data set might look like.
Yeah. Yeah, you could also, you could plausibly extrapolate what the shapes of these things might become if you got many more. So there's a few things I wanted you to notice about what we just did. The questions I asked you were rather underspecified. So there were lots of different valid answers that are sort of fuzzily distinguished by some odd grade of quality. Like, an iris here is pretty good. An iris that's like there is still okay. Here and here would be pretty weird, but you know, plausible, but like off the chart over there is just very unlikely. At least for irises from the same species, let's say. Is here. But if somebody reputable came forth and said, you know, I actually found one like that, you might go, well, you know, maybe. So there's a lot of uncertainty. And the third thing that I want you to notice about it is it's model-based. So whether you are keenly aware of it or not, whether you can articulate the model very well, you did form some model, some impression of what the underlying, what irises are really like based on this limited collection of points, and you can use it to generalize and make up ones that aren't actually in the data. Right? It's not pick one of these dots and say that that's the only one. So let's start coding some code that looks like that. Baby steps, with very close looks at every intermediate point. There we go. So, I need to make that one bigger. Is that good? Bigger? So this is going to be a very dumb, crude model. I'm just going to say, I should mention the form that this is going to take. This is going to be a program that makes up candidate irises. And this one is going to be really bad. But we will look at it. Don't pay too much attention to this garbage. I need to convince my appropriate venture extension that I'm not going to show you to actually talk to the browser. But, okay.
So, what language is this?
Yeah, so this stuff is the scheme-like surface syntax of VentureScript. Do you basically get the shape of this? So point is a procedure that emits four-dimensional vectors whose mean is a 4, 4, 4, 4, and whose covariance matrix is the identity. So it's a spherical Gaussian blob that looks like this.
But
Yeah.
are those the three species plotted, right?
I'm not showing the different species,
Okay.
but yes. And I'm not going to attempt to recover them, because they're actually pretty hard to separate.
Okay.
Well, but here we go. This is a terrible model of irises, obviously.
Huh.
But it's a model of irises, and it has some of the features we noticed. It's perfectly happy to make up new ones. They're not all the same. And it has a sense of like, it is of the opinion that over here is good, and over here is not so good but acceptable, and over here is less acceptable, but actually, trust me, it's not impossible, according to this model, even though it has not yet produced one there.
So are we just going to keep warping this model until it looks like a bunch of irises?
It's going to get better. It's not going to get perfect, because I only have until 9, but it's going to get better.
So just to be clear, you haven't done any learning, right?
No.
Just
No, this is
drawn from this model.
Yeah, this is, and that's what the model says. It says, I've never seen an iris before, and I say irises are that Gaussian blob, and that's what you have.
Well, you did learn those 4
So I
parameters.
personally chose the parameters of this sort of sloppily so it would fit in the plot. Yes,
So you're
but
quite
the
literate.
program didn't.
Yeah.
In any
He
sense.
does have an informative prior.
Yeah.
Correct.
You're
The
just-
prior is quite informative.
You're just throwing darts at a board, pretty much. Okay.
They'll get
Way
slightly
better than I do.
Four-dimensional space.
Okay.
They'll get slightly better. All right, so what do we got here? So one of the, let's see what we got.
Let's start by trying to get the single dimensions into the right ranges.
So I could start fiddling with the parameters, but that's not going to be very exciting.
What about mixture modeling?
We'll get there. Slow. One little baby step at a time, and I hope to be relatively informative about it. I apologize for this piece of stuff. Which doesn't fit right. So this is a snippet that I wish I could have polished more, but I'm going to show this program the irises. Call out to Python, grab the pandas library, read the data file that's the irises for each one, call back into VentureScript with this expression that, yeah, we can do better than that, working on it. But it's going to look like I called your theory of irises and I noted that it produced that one. So we can do that, which is already kind of interesting. You don't usually think of doing this operation. But let's see what happens.
Because I'm not in this field, do I not normally think of using Python, or do I not normally think of
So in this
of
field,
updating my, or of getting information about samples?
in the field, you normally think of both of those, actually. But in programming broadly, you normally don't think of being able to write a program and then say, oh, by the way, I ran you and you did this.
Okay.
So, wait a minute, what you just said, you ran the program and it's observing the output of the program? Or
Yes.
it's observing the data set?
Which, to this model, looks like output of instances of itself.
Okay.
Right, so that is my iris generator, and here I'm calling my iris generator and saying, you made that one. And
But-
this isn't a loop that's...
But it's really coming from,
But this one came from the data set. So, yes. However, you can already tell that that didn't do anything by itself. Which is actually not surprising because the model is quite sure that all irises are generated by this mechanism, namely a symmetric Gaussian blob centered at 4s. And I showed it 150 ones that were over there somewhere, and it said, okay, great. The next one is still packed. But, you know, it didn't crash. Right. It said, yeah, this is good. And actually, if you'd asked, it would have given a number for how little it liked all those irises out there. And that would have been pretty small. Be like, oh, you made me make this up. Didn't learn anything from that. Right, and so
this is going to sound like criticism, and it's not. It's genuine curiosity. Is there an important reason why VentureScript can't read a CSV file and make observations itself? Like, does this need to be a separate phase of execution? Is why this is a run Python to do this, or?
No, I didn't want to re-implement pandas in VentureScript. Basically,
it looks like it's reading a CSV file, which doesn't seem super pandas-y, and I was.
Yeah, so...
Again, not criticism, curious as to whether there's a semantic component to this that I'm missing.
There's a ton behind reading in data frames and getting out to do indexing and sorting.
Yeah, so first of all, parsing CSVs does actually suck.
I'm aware of that.
In the wild. And basically, we just didn't do it. Like, there's no semantic seriousness.
I can come up with a plausible story why that was a necessary and not convenient component of this process. It turns out not to be the one that is the case. That was the question.
Yeah, that's a more convenient way to read data piles is sort of one of those
No,
things.
the thing I just said.
Planning, and it'll get done eventually.
And, you know, this isn't actually that.
I'm satisfied.
Good. I'm sorry if I acted more defensive than I intended
So when
to
you
be.
call this
It's everyone
observe
else.
function, does it get plotted, do those points get plotted in our resulting data set, or?
So the visualization doesn't care about these observes, because I wrote that JavaScript code separately to just grab the same CSV file and display. If that's what you were asking.
I'm saying the model learns even though it ignores so the point of the observes is to let the model learn from them even though it's not actually doing any learning
Yes.
currently?
That would be the goal. That would be the reason why one would do that.
Got it. But multivariate normal doesn't have learning capacity.
So we're going to improve it. We're going to say, well, you know what? That was great. But actually, let's posit a different model of making up irises. Let's say that I don't know what propensity irises have for petal sizes. I'm going to say there's going to be a mean shape, which will be drawn from this Gaussian blob now. And I'm going to say there's going to be a covariance shape. Apologize for the statistics nomenclature here. I didn't do it. Mr. Wishart deserves the blame for this particular distribution.
Indeed.
Now, what's an iris? It is a Gaussian blob again, but one whose location and shape we don't actually know, except that it is to be a blob. And not anything more interesting. Let's get rid of this for the time being. Let's just see what those blobs look like without trying to teach them anything. So here it made one. That is a possible world of irises according to this model.
Sorry, so just to make sure that I'm understanding, what you've done is you're basically, you draw the four means from that multivariate normal, and then the same, you draw a covariance matrix from the Bishard distribution, and then it just does that. So it's not.
And then every iris is drawn from a
Is drawn
Gaussian
from
blob
that.
with the same mean and covariance
Okay.
matrix. But which one?
Training.
Hmm?
It's sort of off by a translation on some of
It's not learning right now. It's just making up worlds. I'm going to show you a different one. It's just made up as soon as I actually started to make it up. There we go.
So in the end, is this going to boil down to just providing like shape and moment restrictions to the model? So like if you're...
That'll get a little more interesting. We'll get to a mixture.
Yeah, I mean, if you want to save it for the reveal, but you know, because it kind of resembles, you know, I mean, not the last one, but the other ones look like, you know, moment restrictions and like kind of non-existent.
Okay, so what is your code currently doing?
Right now, it is making up Gaussian blobs that are centered in about the right place and have a not too crazy ellipsoidal shape.
Based on the observer.
Not based on the observed points at all.
Where did the mean come from?
I made it up.
It's at the top of the file.
He's sampling four means from this multivariate normal, and he's sampling covariance.
Yeah.
Oh, random means.
Right.
Yes.
Because some,
Got it.
some of these questions are about, you know, whether or not there's some like loss function, right? And, I mean, if there's
this
not,
case,
but you know, because the program wants to
yeah.
know.
So
He's not-
this thing is not going to end up optimizing it.
Yeah, I mean, it's just, you know.
The story is going to be posterior sampling rather than optimizing, if that's what you mean.
Sorry?
The story will be posterior samples rather than optimize, if that's what you mean. But you can also do optimization in Venture. We just haven't much.
Yeah, because I'm just wondering, is it, you know, if it's useful to think in like a, well, it's statistical stuff. But go ahead.
I need to go faster. All right. So now I'm gonna get you guys a version of this, to which I will check. But actually, there's a convenient primitive in Venture script for exactly this combination called the normal inverse Wishart normal. So that. This. And the observations to come back. Is that finally starting to look vaguely believable?
Yes.
Good.
Yes.
So, based on the questions I've been getting, I'm thinking maybe I should skip the digression into what happened here. Who wants it? All right, a full of people want it. Stop making more of them. So this was the first little bit of machine learning that we actually saw. It, you know, got some stuff and figured something out. It's not that good yet, but so as you probably inferred from the title, the underlying formalism is probability theory. If you're into jargon, it's doing Bayesian inference on the parameters of the blob. Why probability theory? It has all the features that are needed at this level. It's formal enough to be implemented. That goes a long way. It has the notion of incomplete specification with room to maneuver. So if one writes something like that, the notation means that, whatever A is, it exerts some influence of interest on B, but it doesn't necessarily determine B completely. There's lots of room for possible different B's, but maybe we can evaluate how good or bad they are. And probability theory is happy to answer underspecified questions. At least in principle. That is, if I supply a concrete A, there are possible B's that can be made up in accordance with whatever probability distribution that model is. And the thing that's promising that you presumably recognize is that the famous Bayes rule gives a way to invert models. So the probability of some hypothesis given some pile of observations is proportional to how likely that hypothesis made the observations, how likely the hypothesis is on the basis of everything else, and the constant of proportionality is this how surprising the observations were. So that is, if we can write down this and this, which I did on the previous code block, then this is well defined, at least. And the plot doesn't show the actual hypothesis, it then applies the same data model to generate new points from the probability distribution that is whatever the hypothesis was, and the observed irises. And so this formalism is enough to at least composably define the problem, which is if you had some model of possible things in the world and how they affected things you might observe, you can move to a new model. And
So is the magic that makes it so that information is coming from both directions, does that make NIW normal?
yeah, that thing, make NIW normal includes the analytic solution in the case of this Gaussian inverse Wishart Gaussian interval, so that it can actually jump to the right answer without having to do any significant amount of work.
That's not always the case, right?
It is the case rarely in what you might think of as the wild, but then people intentionally engineer their models to take advantage of this phenomenon when it occurs.
Yeah.
So, in fact, Venture has a large number of primitives that capture that structure so that you can use them. All right. So So now the next step is, this is actually still not such a great model because it's making up lots of clusters, lots of irises in the middle, in the gap in the original data. So we might want to do a little better than that.
Could you show the noise at the bottom of the file again? Okay.
So I will try to go faster. So we can make up a clustering thing instead. Another exciting little primitive. What here? This guy. So the intuition of this is that now we're gonna say that there may be many different kinds of irises. We don't really know how many, but you know, there's a prior. And within every individual cluster is going to be a blob like this, like we just had, but different irises may belong to different blobs, and therefore the blobs may be in different places. That procedure makes up a cluster index, and then the procedure named cluster looks up based on the cluster index, possibly synthesizing a new one, and then the extra pair of parens is to call it to actually synthesize the...
Doesn't cluster ID get used?
It's used implicitly inside the mem combinator.
So if you named it something different...
Wait, so mem is what?
It
Is it just make it so you get
So
the same result?
Yes,
So
it
it's in-
memoizes,
Yeah.
except this is interesting in the stochastic world because you only get one random draw for every value instead of as many times as you called it. But for distinct values of the argument, you get different random draws. And why it's a primitive has a long and funny history.
It lets you do crazy things like ignore your arguments.
It has the effect of having arguments that are necessary to have but not appropriate to include in the body.
What is make CRP?
That is a partition model. The idea is that every call to the procedure returned by makeCRP is an element to be partitioned, and the return value is the index of the element of the partition that it goes into.
So is that going to get the bimodal effect?
One hopes.
CRP's Chinese restaurant process?
Exactly. I didn't know whether you knew that piece of jargon.
No, your explanation.
Crap suffices.
It kind of is. What would you expect to see now?
I'm a little confused because make CRP one suggests, I don't know what it's doing, but.
Yeah, the one is a kooky dispersion parameter.
Okay, so it's not one cluster.
No, it is not one cluster.
One thing, there looks like on some of those that there's a bunch clustered up on the edge. Is that just a render artifact?
Yes,
Okay.
the edge is a render artifact.
Okay.
Anything that's off the plot, I peg to the edge instead of finishing. So is that what you expected?
It's the same. Kind of like it.
It looks like it's less precise, actually. It's getting scattered.
I expected it to look not much worse than the last one.
I bet
So
you did.
I'm satisfied. I think it's great.
Actually, eagle eye over here doesn't very good.
Not much worse.
Not much worse.
I mean, there's thousands of points, so.
The way you described it, it sounds like you've got a cluster. You're making a new cluster for every point. So I must have misunderstood something.
No, it won't actually do that typically. Because the CRP procedure does have a tendency to try to assign things to clusters it's used before.
So if it can assign to a cluster it's used before, it will. But like, what's the basis for that decision, I guess?
Yeah, so this program wanders into an actually rather important idea that people are sort of jumping for, but
Well,
Yeah, I'm sorry.
yeah, no, it's
I mean, it
So
might
are
be.
you eventually gonna get rid of the array 4444? I mean, that seems to be kind of the right
no, I won't. The thing I'm trying to get is to capture the gap between the actual irises. The 444 is less than ideal.
It could be a prior.
Well, so it actually is a prior already. It's not specifying where the blob is going to be. It says, well, I think the blobs are somewhere around here.
So at least we know.
So would a bigger data set if ours at CSV were twice as large, would it have twice the impact?
No, it should stabilize to about the same. Given that the location, the prior for the location of the mean isn't very wrong in this situation, it's not going to cause a major problem. Like if I had said minus 4,000, minus 4,000, minus 4,000, minus 4,000, then there might have been some trouble, but probably not very much.
So it's randomly making a bunch of, I just looked up CRP, it's making a bunch of clusters of random, and
Yes.
randomly assigning points to them. Yeah.
And there's not, like, there's not a way to assign it to a cluster based on any property in particular.
Yeah, so, and that's actually what happens. If you look at what they're actually end up doing, there aren't two blobs the way one might have hoped. Certainly not located where one might have hoped they might be. So the thing this program ended up doing was actually basically assign every point in the data set more or less at random to some partition element without considering where it was. And then said, you, normal, inverse, normal, make a blob out of those. And so all the blobs ended up being in about the same place. Like some other weird one over here. Oops. But that's actually important.
Oh boy.
Oops. Oops. I'm going to do something slightly different. The reason it's important is because this formalism actually lets you ask all kinds of crazy questions. Like you can say, what's the posterior distribution on assignments of my Boolean variables given that I observed that this interesting formula was true? Well, congratulations, you just asked the satisfiability problem. Or you can say, what's the posterior distribution on the secret key that guy was using to encrypt this thing? So there shouldn't be a universal algorithm that solves all of these problems.
Quickly.
Hmm?
Quickly, at least in one case.
Quickly enough to
And
do
less.
during a talk.
And there isn't, right? And there
Probably.
isn't, right?
No, there isn't. So,
There is the guys at 40.
If there was, he would be doing this in a much bigger venue.
or possibly a much smaller one, depending.
Doing it at Fort Meade.
So venture makes things, so venture doesn't act, so the relevance is.
You
So-
seem to have done something useful.
I did. So, in venture, you don't expect to be able to get solutions to all problems. You have to also write code that says how you'd like to attack the problem you just posed. Which is still interesting, and here is an example of a piece of such code. It happens to be very short because I'm using a built-in thing.
What is it
Does that?
talking, like, it's referring to something.
So,
I mean, or presumably it
Yeah.
is because something happened when,
Yes.
something that didn't refer to that.
yeah, so this
Probably.
this is a token meaning actually a historical artifact, but it means do the thing that is called single site Gibbs on the current model. So
What's the current model? All the assumes?
yes, the current
Okay.
model is all the assumes and observes. Assume introduces modeling statements, observe introduces model constraints, infer introduces inference actions.
So is that like running an expectation maximization
Uh,
deal?
Close, not precisely.
Okay.
So operationally, the thing this particular inference algorithm actually does is it starts with some initial assignment of the points that is produced essentially at random, not usefully at random. Picks a point, unassigns it, evaluates how good it looks in every existing cluster, and then assigns it proportional to those probabilities. And the how good now has information from the,
You're talking about the observed points.
yes. Well, yes, all the existing calls to, in this case, the procedure produced by MakeCRP, why do they exist? They exist because they occur inside the observation expressions.
Sorry, so the Gibbs sampling is operating on the clusters generated by the Chinese restaurant process.
Yes,
Um,
correct.
but it's not operating on any of the other like parameterizations of the
Right.
means and normals.
It does not operate on the parameterization of the normals. Those are, the
Because
technical
those are
term is
analytically-
collapsed out.
Sorry?
The technical term for what happened to them is they got collapsed out. The make normal inverse, which are normal primitive, actually internally knows how to compute all the useful integrals with respect to the exact posterior on the.
Okay, sorry, yeah, so basically
Cluster.
because it's sort of, it's analytically solvable,
Yeah.
it does not participate in the Gibbs.
Correct. Or implicitly it does.
But in effect, it doesn't need to change any of its opinions because it already knows the right answer after the fact.
Yes.
So as you reassign those Gibbs, do the clusters
Yes.
norm shape change?
I guess.
Well, I thought
Yes.
maybe
Yes, they do.
I thought maybe it found the two clusters that happened to be to
No.
create that shape.
No.
How
there's-
come they don't just collapse into a single point that would represent the mean for each the mean for each cluster?
why would
I
that-
guess like so if you're for sounding a
It's
point at
because the
random.
observations are where they are and they're not moving, I think is the answer to your question.
Okay.
Yeah,
So-
if I hadn't had observations, actually it wouldn't collapse anyway, it would stay this kinds of vague blobs
But
that you've been
it
seeing.
seems like you unassign a point and then assign it to the next best cluster.
No, I assign it to a random cluster in proportion to how good they are.
Yes, that's what I missed, thank you.
But actually, in this case, even trying to optimize would still find something like this.
Okay, so you wouldn't have it just complete convergence to,
Not on this case.
not on this, okay, thank you.
And then the red points are, every red point is initially randomly assigned to one of these clusters, and basically in proportion to how popular they are in the data.
Yes, that's what I
And then is drawn from that cluster's
From
parameters.
that cluster's
Because you're using
parameters.
CRP, can the red dots create new clusters also?
Yes.
So-
In fact, I think a few of them did over here.
Yeah, but you can't turn that off. Use CRP during, I don't know, switch cluster alloc from being CRP the first part of the algorithm while you're doing observes, and then switch it over to.
Yeah, but that wouldn't actually faithfully reflect the posterior predictive distribution of this model.
The principle of
Because the model says, you know, there's some number of clusters, and there's always a chance that somebody would have made up a new Iris
Didn't know.
that is unlike all the previous ones. Because chance isn't very high. Given this data set, it's going to be something like 1 in 150. But
Can you, are you, in this inventor, are you allowed to write a new distribution? So could you write a distribution that like assigns probability 1 to the number 0 and probability 0 to every other number?
you could.
How would you write
In fact, it's named exactly 0. It is surprising where that is useful, but the reason why it's useful is technical.
And could I, certainly that, and then I could combine that, could I take, is there a way that I could take exactly 0 and exactly 1 and make 1 and assign half probability 0 and half probability 1?
Do you mean that?
And so this is,
You could also use the categorical distribution if you want.
but in particular, this if is not the if with which I'm familiar. This is a special if that makes distribution.
Actually, it's probably more similar to the if you're familiar with than you think.
Okay. Because what I'm getting back is like a distribution, right? Not.
Well, so the mental model you should have is that you're actually coding the sampler.
Okay.
Except some of the pieces of the sampler have interesting additional information attached to them that is useful for doing inference.
Sorry, so,
And in particular, that would have different effects than saying categorical 50-50-0-1, because that one actually knows how likely it was to choose 0, whereas if you ask this guy how likely are you to choose 0, it doesn't, because you'd have to do static analysis on the program to find it, and that's hard.
so one of the ways, and I don't, my familiarity with church and Anglican is small, but if I'm correct, one of the ways in which this differs is that I don't think that, did they support analytic solutions? I thought that they, because my understanding was they were all sampling based. Was that not
I
true?
don't know. In Anglican, I would, I don't know.
Okay.
Now that I've made venture, I know how to put that capability into church or Anglican, but I don't know whether they actually have done that.
Yeah. No, because I mean, I haven't used them too much. I've just sort of read the docs, and my understanding was they were all sampling based. And in fact, most.
I mean, venture is also largely sampling based.
Yeah, I guess there's only a handful of cases that are actually analytic.
Well, we've put in a handful of analytic cases. One thing I'm proud of, especially relative to Church and Anglican, is we have a flexible foreign interface that lets you put in your own things with analytic solutions, with custom inference strategies, whatever.
Yeah.
And they'll mostly interoperate.
Your first step had a few parameters. One, it had the default domain or something. It had scope, default scope, block, one.
Yeah, that's that is a mechanism of specifying where in your model you would like to apply this tactic. So it's it was, the design is a bit rushed. It was necessary to show up at the Pentagon and have this work.
Gotta get that DoD money.
A year and a half ago.
Yeah.
And but what the design is there's a notion of scopes and blocks. Every random choice, every unconstrained random choice that occurs in your model may live in some number of scopes. In each scope, it lives in a unique block. Default is the magic scope that contains every choice, each in its own block. The keyword one means you pick a block at random, uniformly from all the available ones. So what this says is 3,000 times pick a random choice. The only ones available are the cluster assignments of the points, and do the Gibbs thing to it. And then pick another one, and then do that, and pick another one, and do that.
And then it can pick the same one multiple times.
Yes, and it does, because there are 3,000 of them in there.
So when you do you have data that has more than 2 clusters that you can show us?
No.
This will just work on any number of clusters.
Yes.
Pretty much.
Yes. So this is an example of a fairly generic inference strategy that works on any discrete thing, any finite domain discrete thing.
Oh, I was gonna say, what would you officially call this algorithm?
This is the Gibbs sampler
The
for
Gibbs
this
sampler.
model. Yeah.
Okay, thank you.
So, one quick question is there any time that you would particularly think to use this sort of machine learning instead of other machine learning algorithms like neural nets or anything like that? Just, I mean, if you don't have a quick answer for that, you can move on.
Just before coming here, I was at the talk that Dennis gave about AlphaGo and how it beat the world Go champion recently using nothing other than neural nets, and actually more than neural nets. Can't do that with a raw neural net, at least not yet.
It was one dot with like just a single raw neural net.
Huh?
I remember them talking about it during the game, and the policy network, which is just their neural network that predicts what a human would have done in this situation, plays at 1 dot, which means it beats me. Like, it's amazing. Anyway.
Yeah, no, that's the. So I think of neural nets as being a pretty good prior for quickly computable functions, specifically circuits of shallow depth.
Okay.
So functions that are very fast to compute on an extremely parallel machine. And what is that class of objects? Well, apparently good next moves to try and go is in that class of objects pretty well. It seems.
Pictures of cats.
Pictures of cats. Well, ascertaining whether there is a cat in the picture.
Exactly. Yes.
So I guess to add a specific algorithm, how would this compare to doing mixture modeling versus using like expectation maximization?
You could.
But in terms of
expectation maximization in there.
But in terms of would this be a faster, less memory efficient solution to doing that?
Please don't take offense at this answer. I don't care.
Okay.
But the reason I say that is because you as the user of Venture should be able to do any of those things that you are discretion.
I like it. I like
Um,
it.
and in fact, is Gibbs sampling faster than MH, faster than HMC? I'm not in that business.
Okay, thank you very much.
I would like Venture to be a good enough platform where somebody else could figure that out. It isn't. There are things that one might want to improve about it before one actually embarked on a performance measurement project at that level. But
I mean, while we're just asking the theory of performance of these things, are there any asymptotic complexity results published for anything other than rejection sampling? Because I know there was a rejection, rejection sampling is X time in the KL divergence paper
I know what you're referring
last year.
to. In that sense, I am not aware of any.
Okay.
For the benefit of the rest of the audience, there's actually multiple different notions of asymptotic complexity that one might be interested in. One is, I said 3,000. Well, that's a loop. How long does one iteration of that loop take as a function of the data size? And on that dimension, Venture exhibits the correct complexity. That is O1. A different notion of complexity is how large does this number need to be in order for me to get good answers? And does it asymptote in the data size? Does it asymptote in the dispersion of the data, the tightness of the clusters, lots of things like that? The answer to that is nobody knows, as far as I'm aware.
So what about this project that made you choose to write a language instead of a domain-specific language inside of another language, considering the group name, for example?
Why a custom language? Historically, because the people who were doing it weren't into domain-specific languages very much, or embedded languages, and didn't really know good languages to embed in that they liked. And then by the time I came on board, that wasn't a choice I could change. There's an advantage to having a custom language, which is we could do whatever we want in the interpreter of the custom language. We're not tied to any choices that the host made. Which
That
is,
people can't do anything they want
it's a
in your language.
Which is also
Is usually that distinction, right? Usually if you embed, the problem is that you can't control people using the host language when they write programs in yours.
No, he specifically said there's two aspects, right? There's your interpreter can do anything it wants. When it sees this symbol change the world, right? Like,
I mean,
We
there's
have
nothing
taken
about
some
embedding
words
that
of that
precludes
type.
you doing that.
Hmm?
There's nothing about embedding that precludes you from writing your interpreter to interpret any way you want.
It just requires that deep embedding to go back to that.
Yes.
Some people like having syntax.
So, just one final question is, what would be the argument to use this platform over using something like Stan or JAX?
They come with one inference algorithm.
But I can use them for like many inference algorithms.
Stan, no.
No.
Stan, you get Hamiltonian Monte Carlo, you get their particular black box variational inference,
Yeah.
and if those two don't solve your problem, find a new problem.
Sounds like I'll go with yours then.
On those tactics, Stan is going to be a lot faster because it's been much better.
That's what it does.
It does only that.
Yeah.
It's specialized. It's also been engineered longer and by more people.
And despite that, it will perform better.
But there is interoperation with Venture.
That's right. We have there is an experimental module that actually lets you call out to Stan as a foreign process if you really want. It doesn't work very well yet. But
what is it written in Venture?
Venture itself is primarily Python. There's also a second interpreter backend in C++. The error messages are worse, it uses less memory and less time.
Basically, a re-implementation, basically.
Of the core interpreter, but not the fluff around it.
Can you do particularly silly things like define like that? If like could you put lambdas in the then the else cases?
It's a list. Do what you want.
So you can create a distribution over just
Oh, yeah.
functions if you
Oh, yeah.
wanted.
Yes. In fact, a lot of these work. A lot of the built-ins are shaped like higher-order functions, which you could think of as being distributions over functions.
But you can't do the reverse.
It's not. It's
Right.
often fruitful to think about them as distributions over the set of applications of the function it made, because you can actually inspect the function as such. You can just call it. But actually, that idea is very fruitful. You might get a kick out of reading the Gaussian process literature, for instance.
Sorry, so
Oh, please.
I
I like questions.
I have to ask, how would you represent, so there you've got, like one at a time Gibbs sampling from a CRP. How would you represent any kind of graphical model, right? Like an icing model or something? Is that type of thing supported where you have,
Sure, good.
dependencies, almost dependencies?
There's various ways to spell an icing model.
Could you show something like deseparation or some like graphical model in this as well? Or?
I don't have good displays of that. The implementation actually operates that way in it runs your model program tracing the execution and builds what amounts to a graphical model, except it's infinite and conditional, because you never know how many nodes there will be if I take the other branch of the if. And then operates on that. Like so this Gibbs thing is actually a Markov chain whose state space is possible execution histories of the thing. And every step identifies the Markov blanket of that variable. By interpretation, it would be nice to compile that, and only reads that, and that's how it gets the correct asymptotics.
Given all this, can you now query, instead of printing more points, can you query the models that it generated? Ask what does this model now look like after observing all these points and doing the Gibbs reassignments?
So you could
Possibly before predicting all the points and adding to this theory.
You could, I didn't write it to make that easy, but you could do something like inspect what cluster a given point in the dataset got assigned to, if that's what you're asking.
You can't get a list of clusters.
You could. It's a Lisp. Yes.
Can you get a useful artifact out of this at the end? No. I in my head, this looks like the most horribly painful proof assistant experience ever. Modulo the part where there's a goal and then it says, QED. But at the end, in one of those proof assistants, you in theory get this object that you can re-examine and say this is a proof of that theorem. Do you have a representation of, we computed up this model and here's clearly it's a pile of floating point numbers, no one can inspect it. But like, here's a thing, I can pass it around, I can use it. Like, I've generated a useful artifact that is representative of my dicking around here for a while and looking at pictures.
The program that generates samples is a not completely useless artifact in its own right.
So at the end I have my tactic script.
Or you'd have a cost function.
In that sense, yes, but it is more useful than I think you think to have that.
I was actually more interested in how the representation of it seemed like a cool thing. how one would end up with such an object.
Yeah, but the,
But I don't know anything about probability, so I'm looking for things that I know about.
I see.
We need to run.
I'm told we need to get it.
Yes,
So
definitely.
let's say I'm interested in working with, I don't know, like image data or something, right? So the mental model I have here is that I'm sampling, you know, I'm writing a program which will sample like my full image, which is often not how you do machine learning. Right? Usually working with an image data, the first thing you do is like throw